Hello and welcome to another video tutorial on autonomy. My name is George Burke and I'm a research engineer at Argonne National Laboratory, and in today's video we are going to discuss about battery electric locomotive simulation using autonomy for the freight application. Since this is our first video on train simulation, I would like to touch upon some of the basics of train simulation and what are the input that goes into modeling a train, and then we can jump into the battery electric simulation part of it. So let's begin. So there can be three different approach that can be used for modeling a train. So first is the point mass, and as the name suggests, the whole mass of the train is considered to be concentrated at one point, and all the calculation is done taking that into consideration, which is similar to that of the approach that we use for on-road vehicle simulation. The another thing is homogeneous strip approach, where the whole mass of the train is considered to be distributed uniformly along the length of the train. This approach gives better results than point mass approach, but on the limitation side, the coupler forces cannot be the in-train forces cannot be computed using this approach, and if you have an empty car in along the length of the train, the effect of that cannot be considered using this approach. It is slightly more complex than the point mass approach, but the speed is good when we consider the simulation time. And the last one is the linearly distributed discrete mass approach, where you model each and every individual locomotive and car that is in the train, and the advantages of this approach is like the in-train forces can be computed along the length of the train on different couplers, and also uh, you can see the effect of putting locomotive at different remote location along the length of the train. Its effect on the energy consumption can also be studied. So when you are interested in the in-train forces and distributed powertrain configuration, uh, if you want to evaluate the energy consumption for such applications, then this method gives the more accurate results. And in terms of complexity, since we are modeling each and every car and locomotive, it is slightly more complex than the other two methods, and the simulation time is also relatively slightly on the higher side compared to these two methods. But in terms of accuracy, this gives the more accurate results. And in terms of autonomy, like we can do simulation using either point mass or either linearly distributed discrete mass. Both these things we can do in autonomy, but in for today's demonstration I will be using the model simulation using the point mass approach. So moving on, so we started modeling train in autonomy with a diesel electric baseline model. So we have taken Webtech evolution series model as a reference and model the diesel electric locomotive model in autonomy, considering all the main powertrain component which you can see over here. We got the engine, the mechanical and electrical accessory, the generator, the motor, gearbox, and the wheels. And after modeling this, we expanded our model library to include battery electric locomotive and the diesel electric hybrid locomotive and the fuel cell locomotives. So these are the four different technologies that can be simulated in autonomy as of today. And for today's demonstration, we'll be focusing on the battery electric locomotive. So in terms of input, which in general can be applied to all the different technologies, are like the train input data, the locomotive input data, and the route data uh, for running any simulation in autonomy. So these is not the complete list of input data, but only some of the key inputs that are required. So there are some other inputs required other than what is shown here. This is just for reference to know what are the major inputs that are required for simulation. So in terms of locomotive inputs, we need the gross weight of the locomotive, number of axle, max speed, what is the power of the locomotive, and the Davis equation coefficients for the locomotive, Since we are focusing on the battery electric locomotive, you need some cell and module and pack level information, the cell capacity, the open circuit voltage with respect to SOC, the charge and discharge resistance with respect to SOC. You need the traction motor torque versus speed trace and the efficiencies of the traction motor inverter, and the coefficient of friction between wheel and track, the wheel radius, the accessory load, and the gearbox ratio and efficiency map. So these are some of the key inputs from the locomotive side that is required for simulation. And on the train side, we need the total number of cars in the train, and what is the weight of each car, the number of axles on each car, and the Davis equation coefficients according to the type of the car. So for today's demonstration, we'll be using a, a mixed freight train configuration with a single battery electric locomotive that is hauling 26 different type of cars, which is shown here. Like we have the hopper car, the tanker, the gondolas, the center beam, the box car, flat car. So for today's simulation, we'll be considering this configuration of train. And in terms of route data, autonomy requires the train speed with respect to distance and the track grade and curvature with respect to distance. So in this plot, you can see the orange line shows the vehicle speed, train speed variation with respect to distance, and if sometimes this data is not available, then the track speed limit with respect to distance along with track grade and curvature can be used for running simulation in autonomy. So for today's demonstration, we'll be using a route between Amarillo to Clovis, which is in New Mexico, and the estimated length of the route is 101 mile. So you can see how the train speed variation is considered between these 2 points and what is the grade on the track. For this simulation, we haven't considered the curve resistance, but that can also be included if we have the data. So coming to the battery electric locomotive, so while modeling the battery electric locomotive BEL1, we taken the reference of the Webtex Flex Drive locomotive, Flex Drive version 1, and we used all the data that is available on the public domain related with this locomotive to model our battery electric locomotive. That's why some of the parameters you will see that matches with Flex Drive 1. Like we started with a battery capacity of 2400 kilowatt hour, and the actual configuration of cells in the flex drive locomotive is not in the public domain, so we have to make assumptions and create our own pack configuration that we have done, which you can see here, like number of modules in parallel, number of cells in a module, and the number of module and number of cells. And with that, we came with a total number of cell for our configuration is around 19,656, and for the flex drive, according to the data available in public domain, it uses close to 20,000 cells. So we are very close to the actual amount of number of cell that is used in the actual locomotive. And the rated output is 4,400 HP. The gross weight is 430,000 pound, and the number of axles 6, but only 4 are powered. So that's why when you see here the model of the train in autonomy, you can see like 4 motors, but when we go inside the vehicle dynamics block, you can see there are 6 axles are used for the simulation. So the battery pack configuration is assumed because we had limited data, but we try to model it as close as the flex drive one, and try to run the simulation. And it will be interesting to see how far the BEL1 can go with 2400 kilowatt hour. So we'll check that in a moment. So now we can go into the simulation part of it. So I'm here in the Ember GUI in Autonomie, and I will just launch the rail, select vehicle. So inside rail you can see we have different type of models. So the 6 axle 6 motor version is having like all the axles powered, which is like 8 megawatt hour. So we will not be discussing about that. You can see here like 6 motors and 6 axles, but for today's discussion we'll be going into this one, which is having 6 axle and 4 motors. So in the particular uh, configuration of this train, we have various components like you can see here we have the driver, the vehicle propulsion controller, the battery, motors and gearbox, the accessory load. So there are many components into it, but in today's video I will be discussing or focusing mainly on the battery side. So I wanted to quickly show you some of the battery parameters that we have used over here. If you click on the override table and then click eval, so in this screen we can only update the discrete input variables that are required for simulation, but it does require some of the maps which are in vector format, and for changing those data we need to make modification to the initialization file that I will show you in a short while. But here all the discrete input values can be changed, like the number of cells, number of modules, the cell level voltage, and the initial SOC is 100 and the maximum SOC, for some reason I changed it to 90, so I will put it to 100, and the minimum SOC will be 20. So the train should stop when the SOC reaches 20%. And there are other datas also that can be changed, but I'm not going into it. Let's go into selecting the cycle. So we will be selecting the Amarillo to Clovis cycle with grade data in it. So this is how the cycle looks like. The green curve shows here the speed variation, and the and the blue line shows the grade variation. So the total requested distance is 101 miles, and it will be interesting to see how far the train can travel. So from here we will launch the simulation. It will take few seconds to complete the simulation, and in the meantime we can look into the cell data. So this is the cell initialization file, which is a MATLAB script, and here you can see that all the cell related parameters are entered. What is the minimum voltage of the cell, the number of cells in the module, the number of modules in parallel, minimum and maximum SOC. So since we didn't have the actual data from the locomotive, we have made some assumptions based upon the publicly data available in the public domain. And we can see here like we can modify various vectors in it, like what is the internal discharge resistance with respect to SOC, what is the charge resistance with respect to SOC, the open circuit voltage with respect to SOC, and the capacity of the battery that cell that we have used is around like 33.1 amp hour for the individual cell, and the SOC variation with respect to temperature. So most of the things are considered here and entered. There are other input data as well which I'm not touching upon, but the cell can be modeled at a great detail using the initialization file. And I think the simulation is done now. So we can see here that only some portion of the drive cycle is shown, so it means that the vehicle is not able to run completely, cover complete distance requested in the drive cycle. So we can see here like the requested distance was 101 miles and the distance travel is close to 30 miles. So the vehicle is stopped after 30 miles, and mainly because there wasn't any charge left in the battery. So we can see here that the electrical consumption for this route was around like 70,000 watt hour per mile was the energy consumption rate, and The final SOC was 20, so we have set the limit that battery cannot be discharged beyond 20 SOC, so that's why the vehicle is stopped at 20 SOC. The delta SOC is 80 here. And some other insight that we can get is like total amount of regenerative braking recovery for this route during the 30-mile travel. So around 69,000 watt hour of regenerative braking energy is recuperated during this simulation. So in this way we can see how much battery capacity is required for any particular route. So this may vary based upon the variation of grade along the route and at what speed you want to run the train, what is the weight of the train. So all this type of studies can be done using the train simulation in Autonomie. I wanted to show you some more insight like the SOC variation, like how the SOC varies during the simulation. So we started with 100% and we stopped at 20%, and you can see at some point the SOC goes up, and this is mainly during the regenerative phase. So let's see the power out from the battery. Okay, so yes, so you can see here like the uh, the power out from the battery is negative during this period of simulation, and that is where it is recuperating most of the regenerative braking energy, and that's why you see the SOC going up in this phase. There are other uh, braking events where the regenerative energy is being recuperated, but not much compared to what is shown in this section. So in this way, for a particular route, how much regenerative braking energy potential is available can be studied, and the charging point can be decided like after this many miles we need to recharge the battery of the locomotive or change the batteries. Those type of studies can be done using a rail simulation in Autonomie. And I wanted to show you another thing, like a quick easy thing is like what will happen if we reduce the weight on the battery on the train. So that also can be done here, like mass. I will type mass, and so the total weight of the train in this case is 3,700 ton, around 3,700 ton roughly. But we wanted to see if we reduce the weight, how much far it can go. So maybe I will put it to 2,500 ton or 2,500 kgs, and we'll see if we reduce the weight of the train. Then so for doing it correctly, we need to change the Davis equation coefficients as well, like chas the F0, F1 and F2, because now we are letting go some of the cars, so obviously the resistance coefficients will also change. But to do it quickly, I'm just changing the mass of the train and trying to check how far we can go. So I have changed the mass of the train to 2,500 ton, and we'll quickly see how far the train can go and what impact it is going to have on the range of the train. It will be, I hope it will be finished soon. Okay. Okay, we have the vehicle model here. Okay. So we can compare the results side by side in Autonomie, and we will see that I'm hoping to for it to travel like maybe more than 40 miles. Okay, so simulation is done. Great. So this is the results that we see for the train where we reduce the mass, and let's go up and see. Yes, so when we reduce the mass of the train, obviously it traveled close to 11 miles more than the previous one, but again, it the SOC came to the limit of 20% that we set, and the train has to stop. So, uh, so in this way, we can see how far a battery electric locomotive train can go on a particular route based upon the speed target or the speed restriction on the track. One thing which I did not mention is like if you in case if you use the speed restrictions that is given on the track, then autonomy itself decide at what speed the train can travel considering the speed limit, and the speed profile is generated as per that. But in this case we have used the actual train speed velocity on that particular route, so it is done in that way. But the other approach is also doable. So with that, we have come to end of the video. I hope you have got some insight about train simulation using autonomy, and if you have any question, reach out to me, and see you in another video. Thank you.